All right, recording 185. All right. So logarithm and decibels. So decibels are logarithmic, of course. And so this is a kind of a little quick review. Log base 10. See, log doesn't have to be base 10. But that's by far the most common way of us thinking about it. So when it's base 10, it literally just means log is 10 times 10 times 10 times 10 times 10, and so on and so forth. And you could imagine when you keep multiplying things by 10, it goes up, the values go up very fast. And every 10 is even faster. And so it's logarithmic, and that's when people say logarithmic, they mean an increase in count that is certainly not linear. It's well, if you were to graph out a logarithm, it just keeps going up to the point where it's pretty much at some point the increase is almost perfectly vertical because the value is increasing so quickly. All right, so that's what that is. So log base 10 is the most common logarithm, and it's so common that they pretty much just say that's what it is, log base 10. So having said that, I'm just going to go straight to these 3 decibels, and then we'll go into the questions. What's confusing, and I kind of, as I look back, I'm like, okay, I think definitely myself was a little confused on the base 10, and then we get the 3 decibels. 3 decibels technically isn't base 10, it's really base 3. So we think about 10, every decibel is 10. Well, no, it's not quite how it works. So 3 decibels is really, as we know, is either 1/2. In other words, attenuation can be a 3 decibel attenuation. That'd be a negative 3 decibel is equal to 1/2. We really don't have to put the negative in because attenuation is always negative. Or 2 times. In other words, doubling. Now you have to memorize that one. And then you should memorize 10. 10 is actually 10. Well, that kind of, that seems a little obvious to say, but when you're looking at 3 being half, it's like, what does that even mean? Well, 10 is actually either 1/10 or 10 times. Now that means 10 times 10 is equal to 100 fold. So if you have a 10 decibel increase in anything, it's a 100-fold increase. Then you add another 10 to make 20, right? 10 plus 10 is 20. That's easy enough. This would be 10 times 10 times 10. So 10, 100, 100 times 10 is 1,000-fold. So when you increase something by 20 decibels, the amplitude, the strength of that is actually 1,000 times stronger. 30 decibels would be 1,000 times 100 is 100,000. Let's go ahead and write that one. So 10, 100, 1,000, 1,000 times 10. I'm sorry, did I say 100,000? 10,000. And so on and so forth. You see these numbers growing very quickly. That was 30. Just also one other thing to note. A decibels are really ratios. In other words, there's actually, other than the fact that it's a decibel, there's no, I don't want to say no unit. There's no real base. The decibel is always from one, let's say volume. From one volume to the next is a decibel increase or a decibel decrease. If you double if your volume is at 5 and you double it, that's a 3 decibel increase, no matter. So 5 to 10, say, is 3 decibel increase. That's a 2 times. So there's really, in other words, decibels don't stand by themselves, even though we oftentimes refer to a rock concert being 80 decibels. It's actually a comparison between the softest sound you could perceive and a rock concert. So it's always a comparison. Okay. Number 185. You know what? You've got to be kidding me. I am, okay, I am sharing. Okay, good. All right, I'm going to fold my computer. Hopefully this works. I'm going to turn off my forehead. Okay. All right, 185. What is a decibel? So, haven't we spoke about that? And this is more of a memorization thing, but I wanted to go over it anyway. The absolute value of a number? No, I just said it's not the absolute value. A range of values? No. Relationship between two numbers? Yes, it is a relationship. 186. Decibel notation is a blank between two numbers. Difference? Yeah, kind of. A sum? No, a summing is adding, so probably not. Product? No. Ratio? Ratio between two numbers. Yeah, that's more like it. Let's see, what's there? Decibels are calculated by dividing the final strength of the signal by the starting strength, which makes it a ratio. Okay. All right, then I skipped all the way to 194. Let's look at that. Page 462. The intensity of an ultrasound wave is changed by -6 decibels. In other words, attenuation, right? This means that the current intensity is blank as much as the original level. Okay. So you guys don't know off the top of your head what 6 decibels means. But you do know off the top of your head what 3 decibels means. Specifically, 1/2. And you should know, and like I said, the SPI's math is not going to get any harder than this, but this might be it should be math you could do in your head. So if you just think about it, and I'm going to do this, I'm sure you all know this already, but I'm just going to go ahead and say, if we have a pizza and we cut it in half, and then we cut it in half again, 1, 2, 3, 4, we have quarters. So half, and then another half gives us 1/4, so letter C. All right, so that's how you just have to slow down, take that deep breath in, think about it, and say, okay, that's it. 198. Attenuation is determined by which of the following factors? Ooh, I chose this one because that was tricky. Attenuation is determined by which of the following factors? Is it A, density and stiffness? Well, you know, that's a reasonable thought, density and stiffness, because we know that stiffness and density are related. We also know that things that are more dense or considerably less dense have higher attenuation, like bone has high attenuation and air has high attenuation for ultrasound. So A is one of those things that you might go straight to, but let's look at the others. B, frequency of sound and propagation speed. Well, frequency is associated with attenuation, right? Higher frequency, more attenuation. But the speed of sound is the same all around, so that doesn't sound right. C, pulse repetition frequency of sound and path length. Well, path length has something to do with attenuation. The farther you go, the more attenuation, but PRF, what would that have to do with it? It just doesn't make sense. So then you get to D, and you have the sweet spot, path, length, and frequency. So I did this one simply because it would be very easy to go straight to the first one and say density and stiffness. Oh yeah, that definitely causes differing amount of attenuation. And you wouldn't be entirely wrong, but unfortunately for this question, you would. Let's see, why did I do 199? An acoustic wave is traveling through soft tissue. Its intensity undergoes 6 decibels of attenuation. It sounds like the previous one. How does the final intensity of the wave relate to the intensity of the wave when it started its journey? Oh, well, I'm not sure why I did this one, because it's really the same question as, what was that, 194? Yeah. So 6 decibels is really like 3 and 3 decibels. 3 decibels plus 3 decibels. Let's see, I skipped it. 01. An acoustic pulse reflects from a very smooth boundary. Oh, that's right, I drew little pictures here. Where the irregularities on the surface of the boundary are much smaller than the pulse's wavelength. What type of reflection is most likely to occur? So, we have to know the difference between partial. Well, partial is made up. Rayleigh scattering, well, we know Rayleigh scattering only has to do with blood, right? Specular and total, what? To make this harder, they should have put specular and backscatter. Backscatter would be a harder one to look at, but so on that one, I just drew, okay, if my irregularities are small and my wave comes up and these irregularities are smaller than the wavelength, things are going to pretty much bounce directly back. Assuming it's at a 90-degree angle, it could come at a funny angle and then bounce away. That's the thing about specular reflectors, is that they could actually bounce your energy away from you so you don't see it. Whereas backscatter, that's and then backscatter, you have sound. Some sound is bouncing straight back, other sound is bouncing away. but that happens with a little more of a rough boundary. And by the way, most tissue has at least some amount of backscatter. So 201 is a C specular reflector. Oh, this next one. This next one is good just because of the language. 204, what is the uniform dispersion of sound of a sound wave in many different directions after striking a small particle? So I could see that catching you guys. And you're wondering, what does that all mean? A uniform dispersion of sound 204, after striking a very small particle. Okay. Well, all this is saying uniform equal dispersion. That's kind of a direction. So equal directions of sound. So in other words, all they're really saying here is Rayleigh scattering, right? So, but like I said, that's not exactly the wording that I used. It's not the wording that he used earlier on in the book. At least I don't think so. But it's not. He's purposely using different wording to see whether or not you really have it. But you also have to. So you just have to slow down. Uniform. What does that really mean? We all wear uniforms because we're equal. Dispersion. You have to know what that means as well. Let's see. 209. 209. Sound beam travels 9 centimeters in soft tissue. The attenuation coefficient is 3 decibels per centimeter. What is the total attenuation that the sound beam experienced? So what are they asking us? What are they asking? Well, quite simply, what all they're asking, they're giving you everything you need to very easily figure out that attenuation is equal to the attenuation coefficient. In this case, it's 3 times D can be for distance or depth. In this case, it's 9. Well, let's just make sure I'm right. It is, yes, 3 times 9 is 27, yes. Yep. Just remember attenuation. Oops. Okay. So don't freak out. This one's easy. It's giving you all the information you need. We have some others where they're giving you way too much information. We'll go over those as well. Oh, 216 is an example of a perhaps more, not necessarily a difficult equation. It's just a simple linear equation. But it's an example of even though you're not expected to work out mathematically, you will need to know your equations. And that includes impedance and rails. So you will have to remember, or you'll have to brain dump, or you'll have to look at the answers and hope that it jogs your memory. And so that's in microseconds. And God, density. Kilogram per centimeter squared. Anyway, I forgot my units for density there, but that's okay, because now I could answer the question. One should, I guess, what does it say, multiply? Yeah, I'll just put X, multiply the density by the speed of sound. So what's that? B, letter B. All right. I did that one. That's really straightforward, but it's a good example. Got to put those into memory as best you can. $217, which two attribute? Oh, that reminds me, actually. Don't want to forget something. All right, why did I pick 217? Which two attributes help establish the acoustic impedance of a medium? Okay. So that's a little difference. We just figured out that impedance is density times speed of sound. But then we're given the answers, or the question answers are options are density and temperature, density and stiffness, stiffness and elastance, which I'm not even sure is a word, and then elasticity and compressibility. Whoa. Well, let's just guess that we could start by concentrating on density, because if you remember over here, we know that density has something to do with this. So let's kind of, we'll lightly, I'm a little scared to do this. We're going to cross out C and D and then concentrate on A and B. Density and temperature, and density and stiffness. Well, it's supposed to be density and speed of sound. Ah. Speed of sound is determined, the number one determining factor of the speed of sound is stiffness. And actually, number two actually is density. But stiffness is the number one factor on what the speed of sound is. And so if we look at B, density and stiffness. So that's a really sneaky way. It's asking you two questions at once. Whether or not you know this equation and what that equation means, it's also asking you, do you know what makes the speed of sound, the speed of sound? That's a double tricky. 218, which value is closest to the impedance of soft tissue? So you do have to know around 1.6. mega. That is in your book. 1.6 mega rails. So that's something that would be very helpful to have somewhere up in your brain. And if you can't remember the 1.6, remember it's in the mega rails. Just remember it's a huge number. Millions of rails for whatever reason they make the numbers like that. So then we go back and say kilo rails, no. Deci rails, no. 19 mega rails, that might be possible because we are talking about mega rails. But then we look at the next one, 2 million rails is actually the same as saying 2 mega rails. You don't remember what the rails are? That's a very difficult question. Ooh, and was I going to, I have these conservation of energy stuff here. I can't remember if I was gonna do something with those. If I don't hit save, I could destroy the whole thing. Okay. Because the next question I had written down anyway was all the way down to 236. But I think there was some question whether I was going to do one of these. And since which the following describes an angle. Okay. I think all I really want to do here is just a little quick review on conservation of energy. Conservation of energy, assuming no attenuation, assuming that sound goes in a straight line, and it's all those assumptions. Conservation of energy says that the incident beam of sound, the incident wave, has to be equal to the reflected added to the transmitted. So that makes sense. It's, you know, like I said, we're assuming all other factors are nil. Incident has to equal those two together. And there's two basic ratios that we can get out of this. These are all the capital I's are intensities, by the way, I'm sorry. Intensity transmitted divided by the intensity incident gives you the intensity oh my God, I can't remember what C stands for. Coefficient, intensity transmitted coefficient. Oh, thank God. All right. And the reflected divided by the incident is the intensity reflected coefficient. So both of these, incident is on the bottom. Transmitted goes to transmitted, reflected, reflected. So if you want to memorize those. Now this is basically the equations. I don't feel like these equations, except this equation, the top one, is more important. These coefficients are sorry, I don't want to say they're unimportant, but really this one, the conservation of energy, you definitely want to memorize because they will definitely ask you a question about that. And then just a little more review. You guys know this. I have an incident, reflected, transmitted, and not to mention a 90-degree angle. Is this a question of the speed of sound? Everyone's saying no to their computer screens because no, this is a question of impedance. Impedance generally between normal body tissues, the impedance difference is normally very small, which means that the reflected let me make sure I say soft tissue. So soft tissue interfaces, fat delivered, muscled, and interfaces within those tissues, of course, as well. All of those interfaces there's a very small difference. Only 1% at the most, even 1% would actually be very bright on your screen. Or less of the sound wave is returned back to you. 99% or more is transmitted. And that has to do with impedance. Very important to remember the difference because they will ask you, why did this sound beam bend going from tissue 1 to tissue 2 here? This is a question of speed. I'll put that there, make it look like a, whoops. As we know, the reality is speed does change between tissue interfaces. And incident angle versus transmitted angle. Which angle is bigger? Transmitted, right? Speed up means that the velocity I'm just going to C tissue 2 is faster. Okay, it is faster in this case. Speed up, slow down. There are ways of drawing this. So the way I draw this, the arrow kind of goes up, right? That's simply the way I've drawn it. I could draw this sideways and sound coming from a different direction. That appears to show the arrow going down, but that's only an illusion. Always, when I talk about speed up or slow down, what I am talking about is the value of theta t versus theta I. In fact, let's just draw this here. Theta I is less than theta t. I is, in other words, t is greater than I. Speed up. And if I is greater than t, slow down. All right. Just wanted to hit that. Well, let's go ahead and do 236. If I feel like I missed anything, we'll go back another time. 236, ooh, it's a true false. The proportion of the incident intensity that is reflected at a border between two media will increase as the impedance of the media become increasingly dissimilar. Okay. So that's actually a very straightforward question. Might be using some terminology, some ways of saying it that I didn't quite say before, or even Elman didn't say it before. The proportion of the incident intensity that is reflected at a border between two media will increase as the impedances of the media become increasingly dissimilar. In other words, their Z1, Z2 is becoming less alike. When that happens, more is reflected, right? When Z1 and Z2 are perfectly equal, there is no reflection at all. It is invisible to us. Even if there is a border, it's invisible if Z1 and Z2 are equal. But when they're not equal, then there is reflection, and the more unequal they become, the more it reflects. So it's true. 237, a sound pulse strikes a boundary between two media with normal incidence. What does normal incidence mean? Normal, 90 degrees. Okay, 237. Normal, the speed of sound of the two media are very different. However, the impedances of the media are identical. What will happen? Okay. So they're saying Z1 equals Z2 equals invisible, no reflection. And the second part, a little bit tricky here. Let's see, was it the speed of sound are very different. Well, so we don't know how they're different, so we're just going to say C1 is greater than C2. We don't know that. It could be the other way. It doesn't matter. So that means when the speed of sound changes between two media, there's refraction, right? Is there always refraction? Refraction unless you're at 90 degrees. If your incident angle is 0, how do you double it? How do you double 0? It's still 0. So mathematically, you could look at it that way. It's just, and there's just no, if there's no incident angle, then there can be no refracted angle. So what does that mean for 237? They say answer D. There will be, it looks like I went too far. I answered more than we needed to answer. There is no echo, no reflection. Oh, yeah. Here I am answering more than I needed to for the question. We did not even need to answer this part at all. We only needed this to answer that question. Okay, 1017. Oh yeah, we're good. We're good. I think we only have two. I think I only have 2 questions left. All right. Decided to write it all out. An acoustic wave is traveling from medium X to medium Z. Medium X has a propagation speed of 1457 meters per second and an impedance of 1.44 megarails. Medium Z's propagation speed is 1644 meters per second, so it's faster, and its impedance is 1.26 megarails, which is different, but not terribly different, so there'll be reflection, or reflection. The angle of incidence is 32 degrees, and the sonographer ate a ham sandwich for lunch. What is the true angle of reflection? So yes, I added the ham sandwich part, but that is part of the joke. Because when you have a question this long, I could almost guarantee you on the SPI, if you have anything this long, it is filled with information you do not need, right? What are they asking? What is the true angle of reflection? What did we just say up here? Oh, what did I just say? Reflection? Did I just say reflection? Reflection, okay. Let's write that out. All the information we need for reflection is there. Impedance, all the information we need for refraction is here. Speed of sound. Okay, so let's come back. We know that there, I'm getting my words mixed up in my brain. I thought I said something wrong. We know that there will be a reflection. I mean, that's the first question you got to ask. Will there be reflection? 1.44 megarails, 1.26 megarails. Yes, there will be reflection. Now we know we have to ask, what is the true angle? True is thrown in there just to throw you off. What are we going to do, a false angle? It doesn't even make any sense. It's just another word in there to throw you. What is the angle of reflection? The angle of incidence is 32 degrees. At this point, though, it's up to you to know that, oh, actually, it's measured from 32 to be more like this. It's up to you to know that theta I and theta R are always equal. Right, let's see, that's 241. Hope I'm right. Yes, 32 degrees, B. Okay. So what was all the bad information here? I mean, to medium Z, medium X is a prop. We didn't use propagation speed at all. We didn't really use the number, but we know the number was different to the rails, so we'll leave that. Propagation speed and ham sandwich. Yeah, those are all the unnecessary information. All we need to know is that there is a difference in rails and that the incident angle is 32 degrees. We can answer that question. All right. Hopefully this is helping you kind of figure out how to work these guys out. Another true false. People scared of true false questions. Refraction always occurs at the interface between two media when the propagation speeds of the media are unequal. Well, right, yeah. I mean, I just said, let's go back to this little picture. The speed of sound is unequal. We have refraction. Refraction, speed of sound is unequal. There's a trigger word in here, guys. What is that word that you have to be looking for? That tells you it's a trap. Or at least indicates. Sometimes it's not a trap. Water is always wet. Well, yeah, I guess. But refraction always occurs at the interface between two media when the propagation speeds of the media are unequal. This is true in all instances except for the normal. Let's just use oops. All right, well, almost perfect. Not quite. Even though C1 and C2 are not equal, you still will not have refraction at the normal. So false. Stinkers. Gotta watch out for those. And then I think for the last one, I pretty much just copied and pasted this question. Once again, an acoustic wave is traveling from X to Z. Medium X has a propagation speed of 1457 and impedance of 144 rails. It's actually the same exact question so far. Medium Z's propagation speed is 1644 meters per second. Its impedance is 126 mega rails. The angle of incidence is 32 and the sonographer is wearing pink scrubs. Okay, I'm guessing we can get rid of pink scrubs. What is the true angle of the transmitted wave? So once again, the word true is just thrown in there just to mess with you. Angle, what is the angle of the transmitted wave? Okay, so they're asking about refraction. Does it occur? How much does it occur? Which direction does it occur? So if we're asking about refraction, we're already assuming that, well, we know from the previous question that the impedances were different. But we don't need impedance right now. We're just worried about speed of sound. speed of sound and why they have to use, you know, that's another thing. X to Z does not help us. So that's kind of a pain. So X is the first tissue is 1457. Z is the second tissue, 1644. The velocity increases. What happens with velocity increase? Speed up. So let's see what our, does it have, doesn't 248. A is greater than 32, B equal to 32, C less than 32, and D cannot be determined. Well, we can determine. And it speeds up. So it's not, God damn it, it's not equal to 32. It's not less than 32. The answer would be greater than 32 degrees. It sped up. Okay, I think that's it on. Okay. All right, hopefully. That got your brain juices moving. Because now it is time for a Kahoot. I guess we'll do 9 and 10. Five, 1, 2, 14, 15. The beatbox. Okay. What do we call this? 8, 9? Book page. Okay. No, it's not Friday. It's Thursday. I mean, it's not Thursday. It's Tuesday. Oh, yeah. Right. Chapter 9, 10. What is indicated by the letter A? All right, good. Most of you got the near zone show media. Yes, so everything from the transducer face to, well, I'm just going to say that point for now. You all should know what that is, but I'm just going to say that is the near zone, also called the Fresnel zone. All right, next one. CV up front. What area is indicated by the letter? What? Oh, yes. All right. Most of you got focal zone. Focal point is a bit of a trick. You might have misread that, but as you can see, focal point would be indicated by letter B and right at that point, whereas the zone is just an area of higher resolution. Lateral resolution, by the way, right? Okay, focal zone it is. Let's see how we did there. All right. The aperture is 12 millimeters. What is the diameter of the beam at 2 near zone lengths? Yes, most of you, well, the plurality of you got 12 millimeters. Well, I'm not going to say much more other than it goes, the aperture is 12. In other words, the face of the working part of the transducer, the very beginning of the beam, we'll call it very beginning, is 12. At 2 near zone lengths, it comes back to 12 again. Let's see. No, not 6. What is 6? Quick, quick. Good, yes, half the original diameter at the focal point. But that was really short too. Got that quick. Rachel's on fire. Shorter focal point means faster divergence in the far zone. It is true, no matter, so when their focal point is closer to the transducer, the divergence in the far zone is faster. So it's more of an hourglass shape. And that doesn't matter how that focal point is short, whether it's short because of a diameter of the aperture, whether it's short because of the frequency, whether it's short because of you purposely making it short through phasing, electronic. Anyway, no matter why it's short, it'll make more. All right. True or false? Larger beam diameter at transducer means shorter near zone length. Good. Good. Most of you got false. Large beam diameter means a longer near zone length. And that kind of makes sense. Well, there's another one that does not make sense. Let's see if we can find that out. I can't remember if I did that next. Emily's up front. Higher frequency equates to longer near zone length. That surprisingly is true. So just remember, it goes the exact for attenuation. This has nothing to do with attenuation. So higher frequencies, for whatever reason, the way they make their sound beams, they have longer near zone lengths, which is a conundrum because higher frequencies also have higher attenuation. So you would think it'd be the other way, but it's not. Setting focus very shallow decreases far zone resolution. Quick. Very good. Yes, it's true. For the same reason, the fact that a short focus diverges the beam quickly makes our resolution worse. So yes, when you bring your focus very close to the transducer, that's something to think about. You're actually worsening the image in the far zone. Good. Emily's on fire. Single element transducers produce a beam of sound from countless wavelets. All right, we'll review Huygens real soon. That's the crazy thing, is that a single element, if that element is, so single element transducers are not tiny little elements. They're actually quite wide. Not talking about thickness. Thickness is frequency, but they're wide. And when the source of sound is much wider than the wavelength of sound, it acts as if it's 1,000 or infinite number of sound points, point sources of sound. Okay, we'll review that. Extra resolution. First two. But we just barely have a plurality of you saying ability to see reflectors in line with the beam or parallel with the beam. Side by side, that's a different resolution. Behind the beam is not really proper terminology, but we could use that for another resolution. And the ability to resolve images, it's kind of right, but it's not the most right. Good, most of you got, just checking, making sure, most of you got that correct. Spatial pulse length divided by 2 is axial resolution. Does that ever change throughout the beam? I'll leave that to you to think about. Sonographer can adjust it to axial resolution while using the system. I gave you too much time for this one. False. Cannot change axial resolution. The number of cycles is set. And the frequency, that's that, remember, that's just that the way Edelman parses his language. You can't use it, you can't change it while continuously using the system. So that's a tricky. All right, see, he's still on fire. Lateral resolution refers to oh, 100%. Side by side, very good. Why is it not showing those? All right. Lateral, angular, transverse, and all right. LATA, L-A-T-A, is the acronym. Azimuthal is lateral or transverse or angular. Just different words, all mean the same thing. Friday is on fire, this is coming up. Lateral resolution is equal to yes, beam width. Beam width. So lateral resolution is best right at the focal point, right? That's the most narrow part. So 1/2 aperture actually would be lateral resolution at the focal point only. So that's not bad. Axial resolution is the opposite, and slice thickness is the opposite in the forward backward direction. Right. Any is coming up from behind. Lateral resolution is better than axial resolution at the focus. Oh. I think it's kind of the way I said it too. Got you guys. Axial resolution is always, according to our book, and as far as I know, maybe always, but according to our book, axial resolution is always better than lateral resolution, even at the focus. Our phased arrays use external focusing. I gave you too much time. No! We'll go over that. We'll have to go over that again. The phased array. What does phasing mean, and how does it focus? And what does fixed focus mean, and why do we sometimes use a fixed focus? We'll have to talk about that. The word phased in our transducers refers to Yes, it's time. Moving beam lines, it's a little different. Different word for that. Timed is everything in phasing. So when we slight time differences from outside to in, from right to left, for focusing and steering, that is all timed. Right. External focusing uses blank to focus. Oh. All right. Well, I have to say, I have to give credit to whoever put refraction in because technically that's correct too. But a lens, external focusing means that out on the outside of the transducer, there's a tiny, well, you don't even see it, but there's a little lens on the outside. Between the transducer and the skin, there's a lens. Curved element is different type of focusing. I don't think I asked a question. That's internal focusing. A curved element is internal focusing. A lens is external focusing. But refraction of the sound beam is how it works. So whoever put that, you can consider yourself higher in your standing, in the standings. Hello. 20 of 20. Assuming a same number of cycles in a pulse, a 9 megahertz transducer has a better axial resolution than a 5 megahertz transducer. That is true. 9 megahertz. The higher the megahertz, the higher the frequency, the smaller the wavelength. And we're assuming the same number of cycles. So yes, it is true. All right. Shoot. Well played. 54% correct overall. Oh boy, guys. Now you seem to be doing some a little bit better, so that's good. Well, any questions today?
No.
Nothing to ask. All right. Gosh, a little short today. I didn't think I'd be this short. Oh well, because there's nothing else I could really talk about today without being awkward. So instead, let me use my time to continue to get ahead as much as I can so that when I'm gone, you guys are fully engaged. You guys could use your time to do some studying and practice everything. So, all right, guys, we shall see ya tomorrow at 10. And be on the lookout for more announcements. All right, guys, bye-bye.